Hey guys, thanks for watching. In this video, we're going to be going over the week 11 concepts for Physics 111. So starting off with the three different states of matter, we see that solids are going to have a fixed shape and a fixed volume. Liquids are going to have a variable shape and a fixed volume. And then gases are going to have a variable shape and a variable volume. And basically, we can further classify liquids and gases as being fluids. So next off density, we see that for density, we're going to use the Greek letter rho, and we see that density is equal to our mass over our volume. So this is going to give us units of kilograms per meter cubed or grams per centimeter cubed. And then when we're dealing with liquids, we're most likely going to want to use milliliters instead of centimeters cubed for our volume. So we see the conversion here that 1 milliliter is equal to 1 centimeter cubed. So pressure is going to be equal to our force over our area, and more specifically, that force is going to be the magnitude of the force which is perpendicular to our surface, and our area is going to be basically the area of that surface. And this is going to give us units of newtons per meter squared, which we call pascals, and that brings us into atmospheric pressure, which is basically the pressure we experience in an area of 1 meter squared here on the surface of Earth, and basically the weight of all this volume above that meter squared is going to contribute to our atmospheric pressure, and we see that that weight is equal to 1.01 times 10 to the 5 newtons. So this is going to give us, when we divide by 1 meter squared, it's going to give us 101,000 pascals, or 101 kilopascals, 1 atmosphere, or 14.7 pounds per square inch, or psi. Alright, next we're going to be talking about the deformation of solids. So starting off with length, we see that in this example here, we initially started off with an L naught, so some certain length, and after applying this force, we have increased our length by delta L. And we can also see that over in this example, that we can apply sort of a pulling or tension force, which is going to increase our length, or we can apply this like compressive force, which is going to decrease our length. And we can see in this example, when we have the same weight applied to the same length of cable, our actual change in length is going to be different for each cable depending on what the cable is made out of. And basically, in order to account for this, we're going to have our Young's modulus, which is here in our equation. We see that force over area, which in this case we're going to refer to as tensile stress, is equal to our change in length over our initial length times our Young's modulus, which is going to give us units of newtons per meter squared, or pascals. So next we can deform a solid's shape, which we can see in this example here with the bookshelf. If we imagine a very cheap bookshelf, if we were to apply a force at this top corner in this direction, we could imagine that the bookshelf is going to sort of bend in this manner that we have in this diagram here. And we can also see this in this diagram over here. And basically the same thing would happen if we had a really heavy frame hanging on a nail. Initially that nail would be in the wall pretty straight, but after applying this downward force, the nail is going to bend a little bit, and that's going to change the actual shape of the nail. So what we have here is basically, once again, force over area, but in this case we're going to want to call this our shear stress, and that's going to get multiplied by our change in x, or our displacement, over our height, multiplied by our shear modulus, and this is going to once again give us units of pascals. And lastly, we see that we can deform the volume of a solid. And basically what we have here is we have an initial shape here. It was a cube, and we applied the same force to all sides of that cube, and basically shrunk the cube. We decreased the volume of this cube, and we see the same over in this image. And basically we're going to see that our change in P, which is actually our change in force over area, which we're going to call volume stress in this case, is going to be equal to our change in volume over our initial volume times our bulk modulus. And this is once again going to give us units of pascals. All right, so next we'll be talking about pressure from a fluid. And basically to explain this equation over here, we're going to look at our diagram of this beaker on the right. And basically, to start off, we want to remember that pressure is going to be equal to our force over our area. And in this case, we see that our force is going to be our mass times our gravity over our area. So the problem we have here, though, is that normally we're not going to be given the mass of a fluid. Rather, we're going to be given the volume and density of that fluid. So basically, we're going to want to rewrite this as mass being equal to our volume times our density. And the reason why we want to do this is we know volume is going to have units of, for instance, centimeters cubed. And then density is going to be, for instance, grams per centimeter cubed. So centimeter cubed are going to cancel out and we're going to be left with grams, which is a unit of mass. So that's how we basically rewrite mass into units which we would actually be using with fluids. So we're going to rewrite this as our density times our volume times gravity over our area. And then we also see here that we can rewrite volume as area times height. So density times our area times our height times gravity divided by our area. We know these will cancel out. Basically, we're left with pressure is equal to our density times our height times gravity, which is how we get over to this equation. So our P naught is basically just going to be the pressure at the surface of whatever fluid we have. So we're not only going to have the pressure inside the fluid, but also whatever is already pushing down upon that fluid. And the note we can make here is that pressure from a fluid is going to depend on the depth and the type of fluid or the density of the fluid and not the shape of the container. So we have two main ways of measuring pressure that we're going to be going over. We have an open tube manometer, which is this setup here, and we see that we have this equation which was actually derived from this setup, and basically it's going to measure a difference of pressures called gauge pressure. So it's going to measure the difference between this pressure and the pressure we have in this vessel here by looking at this height. And this is the type of setup we would be using when we're measuring our tire pressure. We're actually measuring the difference between the pressure in the tire and the pressure outside of the tire. And then we have barometers, which would be this setup here, and these are going to measure atmospheric pressure using mercury, and the height the atmospheric pressure forces it up a tube. So basically all this fluid here is mercury, and we see that we have this open-ended tube within that mercury, and as the atmosphere pushes down on the mercury, it's going to be forced into this tube, which has a vacuum within it, and basically we can measure the pressure of our atmosphere depending on how high this mercury is forced up into the tube. And then lastly on this slide, let's talk about Pascal's principle, which states that a change in pressure is transmitted equally and unchanged in all directions throughout a fluid. So basically when we have a fluid and we change pressure, that change is going to be equally distributed throughout the fluid. And with liquids, this is going to be practically instantaneous, but with gases, it's going to take a little bit of time. But eventually, this is going to be distributed equally throughout that fluid. All right, next we'll be talking about buoyancy. And let's go through these points as we look at this image up here of this individual swimming. And basically what we see here is that we have pressure exerted on all sides of the submerged individual. And we see that the force underneath the individual is going to have a greater force than the pressure above the individual. And basically this is going to cause a net upward force from the fluid, which we're going to call the buoyant force. And this buoyant force is going to be the difference between the downward forces and the upward forces on the submerged object. So basically let's take a look at this image over here in order to better understand what's going on. We see that we have this upward force F2 and we have a downward force F1 from this fluid. And technically we have a force on both sides as well, but these forces are actually going to cancel each other out, so we're not really interested in those forces. And what we stated earlier is that our buoyancy force is going to be equal to basically our lower force, the upward force, minus the downward force. And when we work through this theorem here, we see that our buoyant force is going to end up being equal to our density times gravity times our volume. And we're going to see this a little more clearly when we look at Archimedes' principle, which states that any object submerged in a fluid is buoyed up by a force equal to the weight of the displaced fluid. So basically here, our density is going to be the density of the fluid, not the object, and our volume is going to be the volume of the fluid displaced. So basically, if we have an object that's completely submerged, then it's going to be basically the volume of that object. But if we were to have an object that's only somewhat submerged, we're only interested in this volume that's under the fluid. Basically, we want to know how much of the fluid is displaced. And then we're going to multiply by our gravity. And we can see that this is going to depend upon the volume of the immersed part of the object, so the volume of water displaced, and the density of the fluid. And we can see an example here where we have two boxes. One is going to be wood and one is going to be made out of metal. And basically they're the same size and shape but different densities. And in the case with the wood box on the left, we see that its density is going to be lower than the density of water. So basically, this means we're going to have a smaller mass, therefore a smaller force due to gravity, and our buoyant force is actually going to be greater than the force due to gravity. So we're going to have an upward acceleration, causing this wooden box to float. And we also know that it's not going to float directly on top of the surface of the water. It's going to be still somewhat submerged. And basically what determines how submerged the object is that with an object that floats, we're always going to have a buoyant force that's equal to our force due to gravity, but in the opposite direction. And then in this example with the metal box, we see that it has a greater density than the water. So in this case, the mass is going to be greater, therefore giving a greater force due to gravity, which is going to overcome this buoyant force, and it's going to cause the object to sink. So it's going to have a downward acceleration. So in this case, our buoyant force is going to be less than our force due to gravity. All right, next we'll be talking about flow rate, which is going to be denoted as Q, and it's going to be our volume over time. So basically, the volume of fluid flowing through a certain area per unit time. And we can see that in this illustration over here. So flow rate will be equal to our volume over time, or our area times our velocity. And that brings us into our equation of continuity. And basically what this states is that when we have a fluid moving through, for instance, a pipeline, we know that our flow rate is going to have to be equal in each section of that pipeline. So basically what we're stating here is that if, for instance, we were to increase the area in a later section of this pipeline, we know that our velocity would have to decrease in order to keep that flow rate continuous. And this brings us into Bernoulli's equation, which we see here. And basically what we can conclude from this is that when speed increases, pressure has to decrease, and likewise, if speed decreases, then pressure will increase. And we have an example of that over here. We know that air is a type of fluid, and basically this is the side view of a wing of an airplane, and this increasing velocity going over the wing is going to decrease the pressure above the wing, and this is going to give us our lifting force. And basically this is how airplanes are able to fly, with this decreased pressure over the wing due to that increase in velocity. And lastly on this slide, we'll be talking about laminar versus turbulent flow. And with laminar flow, it's going to be a streamlined flow where every particle passes in the exact same path as the previous particle. And then with turbulent flow, it's going to be irregular, having random motion. And we can see that in this image of rising smoke here. We see that towards the bottom, we have this sort of straight column. This is going to be our laminar flow, and then towards the top we see that it starts getting wavy, and this is going to be the turbulent flow. Alright, lastly we'll be talking about the differences between ideal and viscous flow. So viscosity is going to be the degree of internal friction within a fluid, and with low viscosity, we're going to have low friction. So in viscous flow, we're going to have flow rate that's slower at the edges and faster in the center, which we can see here with this greater velocity in the center and the slower velocity on the edge due to that friction we have within the fluid. And an ideal fluid is going to be non-viscous. It's going to be incompressible, so it's going to have a constant density. There's going to be steady motion and no turbulence. And with ideal flow, all parts of the fluid flow at the same speed, which we see here on the left. And we see that our viscosity is equal to 0. And this Greek letter here, eta, is going to be what we use for viscosity. And we see over here with Poiseuille's law, our flow rate is basically going to increase as our radius and our change in pressure increase, and it's going to decrease as our viscosity and our length increase, which makes sense because the longer our pipe is, the longer it's going to take for that flow rate to get through, and as our viscosity increases, our friction is going to increase, slowing down the fluid. And then lastly, we'll be talking about Reynolds number, which we're going to denote as Rn. And basically, we have this equation here. We have density times our velocity times our diameter over our viscosity. And it's just important to realize that when we have values less than 2,000, this is going to be our streamlined or laminar flow. And then when we have values greater than 3,000, this is going to be our turbulent or irregular flow. And anytime we have a value between 2,000 and 3,000, we're going to call this unstable. All right, that's all for this video, guys. Thanks for watching.